Hello everyone, my name is Tudor Coman. I'm a software development engineer at Adobe, working in the Bucharest office for the past 7 years. And my presentation today is going to be about dynamic decision making and multi-arm bandits. So, in the AI space currently, we have a lot of popular concepts such as LLMs, embedding models, RAG, and there are still some topics that are not as discussed as these, and the presentation that I'm showing you is with one of these topics. So I'm going to start with a question. What are some necessary skills for a complete AI system? First of all, you have content, which is provided by LLMs. Then you have autonomous actions, which are provided by agents, really popular paradigm lately. And what else do you think is missing from here? And to answer the question, decisions. So the presentation today is going to be about a couple of topics. First of all, I'm going to make an introduction to reinforcement learning. We're gonna make an overview of reinforcement learning policies. Then we're gonna delve a little bit into multi-arm bandits. We're gonna talk a little bit about the different use cases, and from there, we're gonna focus on the study case we performed at Adobe, which was on A/B testing. And last but not least, most importantly, we're going to talk about ways to implement multi-arm bandits in production and how to validate these decisions using statistical significance. So, reinforcement learning. What is reinforcement learning? It's a subset of AI algorithms like machine learning or deep learning. And what this does is basically learning what action to take in order to maximize a reward metric. In simple terms, this would translate in mapping situations to actions. Some unique characteristics about these algorithms. First of all, they are closed loop, so current actions influence later inputs. They also have no training data set or any kind of direct instructions. And the consequences of actions can be longer term, which means that the result is not to be observed immediately. It can, however, but it's not something that's mandatory. And the most common issue that needs to be solved with these different algorithms is balancing exploration and exploitation. Exploration means acquiring new information about the environment of that the algorithm is running in, and exploitation is using the current knowledge to maximize a reward. So policies in reinforcement learning, a policy pi is a mapping from states to actions. This is generally the notation that is used. This policy can be either deterministic or probabilistic. Probabilistic is also the same with stochastic. And these algorithms can be on policy and off policy, meaning that on policy, the agent is learning the policy that it follows, and off policy is when the agent collects data using one policy, which we call the behavior policy, but learns about the optimal policy, which is called the target policy. Generally, bandits with good exploration rates model stochastic or probabilistic policies, because deterministic is very limited in this case. Moving on, about multi-arm bandits. They are a common setting in the world of reinforcement learning. And to basically give the problem in simple terms is that the player has to repeatedly choose between a finite set of actions, while each action provides a random reward from a specific distribution to that action. This distribution is not known before running the algorithm, so it has to be learned from the feedback you get from the environment. The final objective is to maximize the total reward after a certain number of rounds. Now, how is this helpful in the real world? There are a couple of use cases. I haven't delved into these, but they can be applied to healthcare, finding the best treatment while minimizing the side effects, also to finance, but this is not financial advice. In theory, you could maximize the yield of a portfolio by allocating funds to a finite set of instruments. And finally, our use case that we studied was in digital marketing, maximizing a diverse set of metrics such as sales, clicks, or views in an A/B test. What is A/B testing? I'm sure not all of you are familiar with the term, but making a quick overview, an A/B test basically happens when you have a group of users that are accessing your website or web app or any sort of asset like that. And what you want to do is, let's say you want to make a small change in the user experience and you want to validate it by splitting your users in two or more groups. Um, the first group, which we call the control, accesses the same version, so nothing changes, and then the other groups are exposed to some different sort of changes while measuring the same metrics as the control. These are called the treatments. And the goal of an A/B test is to compare the metrics at the end and determine if the change that you wanted to do is actually a good change or not. An example of an ongoing experiment. This is something I found randomly online on Instagram. You can see on the left the old profile layout containing the control basically, and on the right the treatment. As you can see, there is a small layout change in the top, and while they were running this, they were trying to validate if it was a good change. I think it was, because now if you're going on Instagram, you're only gonna see the second layout. Traditional A/B tests generally have a fixed percentage of the traffic allocated to control and treatments. For example, you could have half of the users in the control and the other half in the treatment. Of course, this is not something that is a general rule. You can play around with these allocations depending on your goals. And generally, each user is allocated with a pseudo random number generator, and this information is stored in order to be consistent. You wouldn't want a user today to see the control, tomorrow to see the treatment, and the day after to see the control again, because that might affect your user experience negatively. One of these traditional tests is meant to determine or validate a single hypothesis, and there are a couple of advantages and disadvantages for this. Advantages are that it's very easy to implement, and the statistics behind is easy to compute and explain, since we are not playing around too much with the traffic allocations. However, there are some disadvantages, because in this case it might take longer to reach a statistically significant hypothesis, and it's also a slower approach to evaluate multiple ones due to the fact that you're limited to validating one at a time. Now, going back to multi-arm bandits, um, you can add these multi-arm bandits to a traditional A/B test by transforming that static allocation into a dynamic one based on real-time performance. This approach basically uses reinforcement learning to be more adaptable to user behavior, and is also useful for delivering personalized content. I'll get back to the personalized content a bit later, but for now, let's focus on the advantages and disadvantages. Advantages are that you can identify much faster what the winning variants are, and you're helping the marketer or whoever is running such a test or experiment to iterate through more hypotheses. But the disadvantages are that, of course, introducing this will lead to more advanced statistical concepts. And a problem we discovered was a potential overfitting to short-term trends. This can be mitigated, however, by how you calculate your metrics and how you manage the bandit policy. And due to this overfitting, another disadvantage that results is suboptimal exploration of lower performing variations, which might make you ignore a variant that might be better on the long term. So what we tested, we took some traditional experiments where we added multi-arm bandits and transitioned the manual allocation to a dynamic or automatic version. Uh, Basically, our goal was to find the winning variant in an ABC test with the following conversions: 6%, 2%, and 4.5%. These are totally arbitrary. We just wanted to see how a bunch of algorithms perform in this case. And here's a list of the algorithms that we used. I will not get very much into detail. I'll provide some resources if you are more interested in delving into the specifics of these algorithms. But here is a result overview of the algorithms. As we can see, we have some plots, and we basically wanted to show the percentage of allocation to the winning variant, which was the first one with the 6% conversion rate. And we wanted to see how these bandits performed. Um, we see that some approaches are more gradual, such as the top left one. Some are more aggressive, like the top right one. And some do some exploration as well and then transition to an exploitation mode. Um, some high level conclusions that we derived from these simulations. We found some interesting facts after also doing some more testing. There is no single algorithm that works best in any setup. So, depending on yours, you might want to a test like we did to see which approach works best for your use case. Some algorithms are prone to overfitting. This happened in our case with Thomson sampling that I presented earlier, the top left one. A way to mitigate or avoid overfitting is to constantly update your metrics, like a sliding window or something like that. And in some cases, cold start can be an issue. If you don't have enough data to start, your bandit will basically perform like a random allocation until it gathers some data. Taking this approach further, you can add context to multi-arm bandits, such as users' location, age, preferences. Depends very much on the data that you have on hand. This would be called a contextual bandit because it uses some more context information. The context is integrated into the policy through embeddings. You can use a variety of embedding algorithms. Like I said before, whatever works best for you is what you should do. Advantages here are that targeting the right users with the right personalized content. Like I said before, you can use this for personalization as well. Especially if you have such parameters, you can create different variants for segments in your audience and determine which work best. And basically, having this information also results in more insights into user behavior. But the disadvantages here are that it's an even more complex setup than the one presented before, and of course, you need more data. Now to the most important part of how do you implement a multi-arm bandit in production. There are two ways. You either choose to do an online policy evaluation, but for this you need a fast reporting engine to compute metrics all the time, or to have the metrics already computed when you want to make the decision. Making it online basically means making it on the spot, so you need a very low latency, and if you don't have it, you have to trade it off for the advantage of better accuracy. And you also have offline policy evaluation, which requires like a scheduled or cron job to compute the metrics and the policy on a frequent basis. This could be once every few hours, daily, even weekly, but it really depends on what accuracy you're trying to achieve. But in this case, you're trading off this smaller accuracy for a much better latency, especially if you have more complex metrics. Validating how a bandit works is very difficult, and there were some very interesting discussions at the event about this. One of the ways to do this is with statistical significance, so determining the right sample size of your decisions. In plain English, this means that for something to be statistically significant means that the probability that an observed effect or difference is not merely due to random chance, but is actually a genuine phenomenon. Of course, if you have a very small sample compared to your needs, it might be something that occurred due to random chance, and you wouldn't want to take decisions based on that. As I said, this is one of the ways to validate the behavior of a multi-armed bandit, and you want to avoid sampling errors by gathering enough data. The metrics used for this are confidence levels, p-values, type 1 and 2 errors. Of course, you can look at more, but these are the most common ones. To make a quick overview, confidence levels are basically the probability that your test results are not due to random chance. We typically set this at 95% in our A/B testing use case. P-value is the exact opposite, where it's basically a measure of the probability that the observed results occurred by random chance. And type 1 errors are false positives, and type 2 are false negatives. I included some examples that are very easy to understand, maybe not the happiest, but they're very easy to make an analogy. Sample size. In simple words, there's no point in running an experiment after the sample size has been reached. You have gathered all of the data you need to take a decision, and setting some target values for the previous metrics, you can calculate the sample size beforehand, knowing the configuration. I also included an example with some of the metrics that we use, such as the baseline conversion rate, minimum detectable effect or lift, confidence level, power, and an allocation ratio between your variants, and you would get an output like something like, in this case, 4,400 users. For calculating this, it really depends on your setup. Normally, for a fixed allocation A/B test or traditional one, the sample size can be calculated mathematically based on the parameters I just showed you. But you can also calculate it for multi-arm bandit algorithms. This is a bit more difficult because these algorithms are not deterministic. As I said, you're talking about probabilistic policies, so you will need to do some simulated runs in a Monte Carlo simulation method or something like that. You can calculate an approximation of how many users you need. In this case, the calculation is should be done before letting a bandit off the hook. So you know, like, how many decisions need to be taken in order to make sure that the bandit uh, takes informed and correct decisions, but at the same time you're leaving space for adaptability in case something changes in the environment. Some key takeaways from this presentation: decisions are equally important when building complex AI systems, and multi-arm bandits are a great way to optimize decision making across various sectors using AI and reinforcement learning. There are a lot of initiatives and research literature on the subject about contextual bandits, collaborative bandits, and so on. And one way to know how many decisions need to be taken before the bandit can take statistically significant ones is through sample size calculation. If you're interested in doing some more reading on the algorithms, if you're passionate about the statistics and mathematics behind it, I've listed here some papers that we used in implementing our algorithms. You can check them out. They are pretty advanced, but it will get you like a much deeper understanding of the policies and how these algorithms work. Thank you very much for watching this presentation. If you enjoyed it, or if you have some questions, please check out my LinkedIn page by scanning the QR code or entering the link. We can connect over there and have some deeper discussions about this topic if that's interesting for you. I might have some input on other topics related to AI or machine learning. This is basically what I'm focusing on at Adobe in building and designing production ready AI systems. So if you have any questions regarding that topic, uh, you know where to find me. Thank you very much, and have a good day.